thank you very much. My name is Ross Bennett-Kennett. I'm an undergraduate from Arizona State University, and I've been working with this group for about 3 years now on this process of nanobonding that I'm going to talk to you about today. Okay. So just a little outline of what's going to happen. About 17 slides, so I'll try and go through it quickly. What is nanobonding, and then what is the synthesis in our steps? So we create a precursor phase, optimize the contacting in a class 10 hood, optimize the compression to flatten out any warping in our wafers, and then anneal with a temperature under 180 degrees in a steam catalyzed environment. And then a new technique that we've developed is to apply an optimized DC electromagnetic field and then tune the field to an RF AC in order to correct for any built-in voltages on our samples. So then part of the talk will go over the characterization of these precursor phases and then the post-nanobonding samples. Okay. So here is the essence of what we're doing. We're controlling the silicon surfaces at the nanoscale, creating a highly planar ordered surface phases, so that's the definition of our two-dimensional surface interface, and then control the hydroaffinity, and that's a way that we can characterize this is by understanding the hydroaffinity of surfaces. And what we find is, and our goal is to create these hermetic wafer seals via these molecular bonds that occur when we have these conditions met. So this is important in medical implants and then marine or air probes where that hermeticity is going to be important for the lifetime of the device. Okay, so this is the precursor phase that we're dealing with. We have a silica wafer with dangling bonds that we've etched, and then an Si-100 wafer on the other side with an ordered oxide, flat ordered precursor, again, the two-dimensional model. And our goal then is to cross-bridge via our hydroxylated SiO2, forming the nanobonding two-dimensional phase. So this is some evidence of our highly ordered oxide on the Si-100 surface. And here we have some images of the high-resolution TDM showing a step density of 20 nanometers after our ordering clean, as opposed to 2 nanometers in a native SiO2 on Si-100. Again, some additional evidence here in the infrared. We show that our bond lengths for about 8 angstroms of thickness are relatively uniform, again showing order on the surface. Okay. Another evidence for this is then the hydrophobicity or hydrophilicity of the wafer. Our dangling bonds thus are going to attract liquids like water, while our ordered surfaces are going to repel and create more hydrophobic droplets on the surface. Okay. And then the actual synthesis occurs in a class 10 clean room and hood, where we contact the surfaces that have been prepared with both precursor methods, and then the application of steam in order to create a optimized humidity for the bonding process. And some examples of post-nanobonding and some evidence that we actually do have bonding aside from the contact. We see here higher roughness where we had a sample placed to be bonded, which you can tell by the hydrophilicity of the water there, as opposed to on just the annealed silicon. And then additionally, we would expect after ripping apart the wafers that we would see a higher oxygen yield on the silicon side due to the deposit of the oxide. And again, in our ion beam analysis of this, we see a higher oxygen yield on that wafer. And then looking at the atomic force microscopy images of our surfaces to understand greater our order and what's actually going on, we have 3 different surfaces here, or 2 different surfaces, and then a post-bonding. See an increase in roughness on the post-bonding, again, evidence of the actual bond. And then we have 20 nanometer peak density or atomic terraces on those surfaces as the highest density. So again, showing the order of the surfaces. And then again, this is on the similar thing. Again, nano-bonding and debonding of the silicon dioxide, high roughness, which is going to show the deposit of the oxygen. Okay. And another technique used is, and that we have analyzed, is the difference between a spin etch and a normal wet chemical bath etch, submersion. And we see that with the spin etch, we have a peak density of around 30 nanometers. So we are again increasing, instead of from 2 to 20 nanometers, we are increasing that terrace length to about 30 nanometers, which is a large improvement. Okay. An additional form of characterization that I've worked most on is three-liquid contact angle, and this is to determine the actual surface free energy of our samples. These equations sort of go over the theory of what's going on. We measure an ellipse of our liquids on the surface, use 3 different liquids that are intended to sort of pinpoint which portion of the surface energy, either the van der Waal, the donor acceptor portion of the free energy, and we use 3 liquids to create 3 equations, 3 unknowns that will give us the information needed to determine the surface free energy of our sample. Okay, so combined, we have these equations that relate the angle of our liquids to some known values for the liquid, and then our unknowns of the surface free energy. Here's a little setup of what we do, how to do it, a little bit low tech, but we use a pipette to drop our liquids onto the surface with controlled volume to reduce the effect of gravity on the droplet size and the angle. And then we use a camera up close to take some images of our droplets on the surface. Okay, and then our 3 liquids we use are 18 megaohm DiH2O, and glycerin, and alpha-bromonaphthalene, which is our non-polar liquid, which helps us to determine the van der Waal force, or the van der Waal interactions of the surface free energy. So what you're seeing here is a reflection of the droplets with the wafer here underneath on both sides, and then you have the actual droplet forms up top, and its reflection helps us determine the angle with our ellipses analysis. Additional process steps that we take is sonication and rinsing of the glycerin and the alpha-bromonaphthalene to ensure that the surface is the same before as after when we do the actual contact with the liquid. And then here's some results that we have found of this analysis that's actually pretty telling about the success of our goal in the nano-bonding. So comparisons we have here of our before and after, we see that we have greatly reduced the surface free energy of this is our ordered SiO2 on the Si100, so that's our precursor phase, compared to an as-received wafer. It has a higher value for the total surface free energy. And this is all in millijoules per meter squared. Okay. And then we have measured the actual characterization of the surface after a dry anneal and a wet anneal. And the wet anneal, again, is what I mentioned is the steam optimization for the humidity. And we have found a bonding rate only to be 10% with the dry anneal, but the addition of the steam has increased the bonding rate to about 75%. And what we can learn from that is understanding these surface free energies and what has changed. We can understand better what our surface needs for that bonding condition to occur. What we see is essentially an elimination of the donor component and an increase in the acceptor component of the beta cristobalite on the SiO2, and that is essentially the optimization of our bonding, is the increase of acceptors and the reduction of donors for our surface free energy. Okay, so with all of that information, we've sort of put together a model of what we believe is occurring as this 2D nano interface. And you see again, we have our precursors on both sides, and we create this SiOX two-dimensional film between that bonds them together. And that is essentially what we have been doing, and just some acknowledgements if you guys have any questions.
Okay, well, thank you very much. How thick are your wafers, your entire wafer?
The entire wafer?
Yeah.
Trying to think. We use, well, let's see, let's go back. We use standard, I think, 6-inch wafers, 4-inch wafers.
Okay.
I think we use 4-inch wafers for the diameter. I'm not sure about the thickness, honestly. Here's sort of a image to give you a better idea. I don't think we've measured the thickness, and I don't know it off the top of my head. Sorry.
The structure that you showed at the end,
Yeah.
is this derived from some type of analysis or modeling or both?
We've done some, actually a grad student who graduated, his thesis was on the actual modeling and the crystal, the stress on the actual silicon crystal that would occur, and sort of optimization and understanding of what that model has to be and what are the possible tensor stresses on the actual crystal structure. So, I mean, it's been, what?
The stresses were measured, or how was it?
They were using a model on the actual crystal structure itself to understand what the stretch would have to be in order to actually bond those two together to make them match across the surface. So that was done by him, and the model is the best possible solution for what we found, what he's able to find. So.
If I may just have a very quick follow-up question. The Japanese device should be understand some exactly what I was saying. But let's put Japanese as well as passive.
Looks like I believe so.